Okay, so I've copied here the blue boxes from 7.3. Make sure you read the section thoroughly and understand what the composition operation is between functions and sort of how it plays with inverses and identities and so on. So let me just give you some commentary here. The image you want to keep in mind for composition is as follows. You've got some sort of domain X for the function f, and its codomain is a set y prime. And then you've got a second function that you're going to apply to the outputs of f. So the domain of that second function g, we call y, must contain the outputs of f. The function g goes into its own codomain z. So the image is that you take elements from the sort of first domain, elements x, and you run them through the f function, and then in turn run them through the g function. If we think about composing functions with special functions like identities or inverses, let's just think through why these statements would be true. If you've got a function f from x, let's say, to y, and we consider composing f with the identity in a couple different ways, we get the following results. So there's an identity function on the x set, which I can draw like this. The domain and the range of the identity function is the set x. And of course, y has its own identity function, iy. And we can compose in a couple different ways. If you first run an element through the f function, and then you run that result through the identity of y, then you're going to get back to just the f of x. So again, starting with an element x in the domain of f, running it through the f function and producing f of x, and then running f of x through the identity on the set y gets you back to f of x. So that's just a fancy way of saying, let me correct my font here. That's just a fancy way of saying that I sub y, the identity function on the set y, composed with f is simply just f. So if you run something through f, then through the identity, it's the same effect as running it through f. And then, of course, if you start with an element in x and run it through the identity first, so start with an element x, run it through the identity, it brings you back to x, and then run it through the function, it's going to bring you to f of x, exactly the same effect that f has. Okay, and then we can think about these next two results just intuitively as well. I can make reference to this diagram up here. If f happens to be 1-to-1 and onto, then it has an inverse like this. And what this is saying is, if you start with an element x and you apply f to it, it brings you to f of x. And the inverse function applied in turn will bring you right back to x, which is exactly the effect of the identity on the set x. And if you go in the other direction, if you start with an element in y, let's say, and you apply the f inverse function, it's going to bring you over here to f inverse of y. And from there, if you apply the f function to that result, it sends you exactly back to y, which is the effect of the identity function on y. So little y starts in y and gets sent right back to itself. That's what the identity does. Okay, so lastly, some actual results that may need a little bit more arguing. If you've got two 1-to-1 functions, then the composition ends up being itself a 1-to-1 function. So this is worth going through a proof of this thing. It's a good exercise in focusing on what you're supposed to focus on when you're proving that something is 1-to-1. Okay, so suppose that we have two 1-to-1 functions, f and g, and then I focus on what it is I'm trying to prove. I'm trying to prove that this other function, g composed with f, is 1-to-1. So how do we do that? You're supposed to suppose that two image elements are equal to each other and try and deduce that the domain elements that they came from are equal as well. So I start by supposing G composed with f of x1 is equal to G composed with f of x2, and I hope to make an argument that x1 equals x2. So x1 and x2 are supposed to be domain elements, and I notice that my assumption, by the definition of composition, the equation that I'm looking at is this. It's G of f of x1 equals G of f of x2. Now, since G is a one-to-one function, it must send it sends fx1 to the same place as fx2, means that fx1 and fx2 must be the same thing. And so I get to write that down. F of x1 must equal f of x2. And furthermore, since f itself is one-to-one, and the fact that fx1 is equal to fx2 means that x1 must equal to x2. It's a good exercise for you to prove Theorem 734 on your own by carefully focusing on the definition of onto. One last thing, I thought that you might want to type the composition symbol in LaTeX, and it's \CIRC.